Welcome back to the deep dive. Ready for another deep dive with me?
Always.
Awesome. Sometimes you come across a research paper and it just changes everything.
Oh, yeah, for sure.
And today we're diving into one of those attention is all you need.
Definitely a game changer.
This paper introduced the world to the transformer, a neural network architecture that's completely revolutionized AI.
Absolutely. And especially in areas like machine translation.
Yeah.
I mean, what's really fascinating about this paper is it kind of challenged everything we thought we knew. Back then, everybody was all about recurrent neural networks.
RNN.
Yeah, RNNs for sequence transduction tasks.
Yeah.
But the authors of this paper, they saw the limits. I mean, RNNs process data one step at a time. It creates a bottleneck.
It's like reading a book one word at a time.
Exactly.
You miss the flow.
You miss the connections between ideas. You totally lose the big picture.
And the bigger the book, the longer it takes.
Right.
And in AI, the data sets are massive.
Huge. So that slowness is a real problem.
It's a huge problem.
And so the authors of Attention is All You Need had this radical idea. What if we just ditch recurrence?
Whoa. Okay.
What if we find a way for the model to just see the whole sequence, like our brains can? And that's where attention mechanisms come in.
Okay, attention mechanisms. Break that down for me.
So it's kind of like, imagine you're reading a sentence and you focus on certain words to understand it.
Right.
That's essentially what attention mechanisms do. They allow the model to focus on different parts of the input and kind of figure how important they are.
Gotcha. So instead of going word by word, it's looking at the whole sentence at once.
Exactly.
And understand all the relationships. Did they ditch convolutions too?
Yeah, they did. It was a really bold move.
Wow.
But by just using attention, the transformer could be trained way faster.
Okay.
And here's the kicker. It achieved better performance on tasks like translation.
That's huge. So much faster and better.
Yeah.
Okay, this is where it gets really interesting for me. How does attention actually work? I mean, we're talking about different types. So, right.
Yeah.
Scale dot product, multi-head attention. What's the deal with all that?
Okay, think of it like a team of expert translators, all working together. Each one is focusing on a different part of the sentence.
Okay.
So one might be looking for verbs, another one's looking for nouns, another one's looking for the connections between words. That's kind of what multi-head attention does. It lets the model capture a much richer understanding of the language.
So each head is providing a different perspective.
Yeah, exactly.
And together, they get the full picture.
Yep.
Okay. Let's try to visualize this. The paper has that diagram, figure 1, showing the architecture of the transformer.
Right.
What are we looking at here?
So there are two main components, the encoder and the decoder. Think of them like two engines working together. So the encoder takes the input sentence and processes it, extracts all the information, and then the decoder, it takes that information and uses it to create the translated sentence.
Okay, so we've got these two engines, and inside them are the attention layers.
Right.
And some other stuff too, right? What is positional encoding?
So unlike RNNs, the transformer doesn't automatically know the order of the words. Positional encoding is basically like giving each word a number. So the model knows where it goes in the sentence.
It's like your word number 1, your word number 2.
Exactly. Otherwise, it would all get mixed up.
It would be a mess.
A total mess.
Okay. The paper also mentions feed-forward networks and something called embeddings. Remind me about those.
So embeddings are like a way to represent words as vectors, basically lists of numbers that capture the meaning of each word.
Okay.
And then feed-forward networks, they take those embeddings and process them further. They're like the gears that refine the raw materials.
Okay. So we've got attention layers, positional encoding, feed-forward networks, embeddings, all working together.
Like a well-oiled machine.
But the paper makes a big deal about self-attention, being the star of the show. They even have a table 1, comparing it to recurrent and convolutional layers.
Right.
And the differences are pretty stark.
Yeah, they are. What's amazing is how self-attention is just better in terms of computational complexity, parallelization, and path length, especially when the sequence is shorter than the representation dimensions, which is often the case with language.
And that leads to faster training times and better performance.
Exactly.
It's like comparing a bullet train to a horse-drawn carriage.
Perfect analogy.
Okay, this all sounds amazing, but I've got to ask, how does the transformer actually perform in the real world? Do we have numbers to back up all this hype?
Oh, yeah. The results are seriously impressive.
Okay, good.
Let's look at Table 2 in the paper. On the WMT 2014 English to German translation task, the transformer got a BLEU score of 28.4. That was a new state-of-the-art result at the time.
Wow.
And not only did it get better results, but it did it with way lower training costs. Like the paper says it only took 3.5 days on 8 P100 GPUs, a fraction of the time and resources of other models.
I'm starting to see why this paper was such a big deal.
Yeah,
Okay, so it's great at translation, but what about other tasks?
right.
The paper looks at English constituency parsing too, right?
It does, which
Yeah.
is a totally different challenge.
Yeah.
It's about understanding the grammatical structure of a sentence.
Okay, so how did the transformer do?
It did amazingly well. They
Mhm.
trained it on the Wall Street Journal portion of the Penn Tree Bank,
Okay.
which is like 40,000 training sentences.
Mm.
And then they tested it with a way bigger data set of 17 million sentences.
17 million. Wow, they really put it through its paces.
They did. And in both cases, it got amazing results. It even beat some really sophisticated parsing models.
So it's not just a one-trick pony.
Correct.
It's a powerful tool for all sorts of problems.
Absolutely.
Okay, we've covered a lot. Let's take a minute to think about what we've learned about the transformer. What are the key takeaways?
The most important thing to remember is that the transformer is a completely new way of thinking about AI. It moves away from the old way of processing things one step at a time. It embraces attention. So models can understand and process information in a more holistic way.
It's like AI got a new set of eyes.
Exactly.
Eyes that can see the whole picture.
Yes.
And this leads to all these breakthroughs in different areas.
Definitely.
This is just the beginning, though, right?
Oh, yeah. There's so much more to uncover
Yeah.
about the transformer and what it can do.
Stick with us. We're going to go even deeper.
We'll be right back. You know, one of the things that really struck me when we were talking about the transformer's efficiency is how it connects to, like, human cognition. Our brains don't process information like a computer program. We jump around, we make connections, we focus on what's important,
Yeah.
and attention seems to capture that.
That's a really interesting point. It's like the transformer is mimicking how our own minds work. And it's that attention that allows it to be so efficient. You mentioned earlier how the paper compares self-attention to other techniques. In terms of computational complexity, parallelization, and path length.
Right.
Can you explain those a little more? I'm not sure I fully get what they mean here.
Yeah, absolutely. So let's start with computational complexity. That basically means, like, how much computational power you need to do a task.
Okay.
And the cool thing about self-attention is that it can connect all positions in the sequence with a constant number of operations.
So it doesn't matter how long the sequence is, the computational cost is kind of the same?
Yeah, pretty much.
Yeah.
Especially when the sequence is shorter than the representation dimensions, which is often the case in language stuff.
Wow, that's efficient.
It is.
Mhm.
And then parallelization, that means doing multiple computations at the same time.
Right.
And again, self-attention is great for this because it doesn't have to process things in order like RNNs.
It's like having a whole team working on it instead of just one person. Okay, and what about path length?
So path length is like how many steps it takes for information to flow through the model.
Okay.
With self-attention, that path is way shorter because each word can directly attend to every other word.
Mm.
So the model can capture long-range dependencies better, which means it understands the context better.
It's like having a direct line of communication between all the different parts of the sentence instead of having to go through all these middlemen.
Exactly.
Now, the paper also talks about restricted self-attention
Right.
for when you have very long sequences. What's that about?
So imagine you have a really long sentence, like a paragraph or even a whole document.
Yep.
Having every word attend to every other word would take forever, even for the transformer.
Yeah, that makes sense.
So with restricted self-attention, you just limit the attention to a smaller area around the output.
Mhm.
That way, it's still efficient, but it can still understand the context.
It's like telling each word to just focus on its neighbors, not the whole neighborhood.
Exactly.
Okay, I get it. It's a compromise. You get efficiency and effectiveness.
Yeah, exactly. And it shows how flexible self-attention is. You can tweak it to fit the task.
What I find really exciting about self-attention beyond its efficiency is that it's more interpretable. With RNNs, it was hard to understand why the model did what it did. But with self-attention, you can see the attention patterns.
Yes.
You can see which words it's focusing on and how those connections lead to the output.
It's really cool. And the authors of the paper, they actually looked at the attention distributions from their models.
Oh, interesting. And what did they find?
They found some really interesting patterns, like connections that seem to reflect the grammatical and semantic structures of the language.
So it's not just random connections, it's learning something meaningful about the relationships between words.
Yeah, it is.
That's amazing. And they even have some visualizations in the appendix,
They do.
showing how different attention heads focus on different parts of the sentence.
So some heads seem to be really good at spotting verbs, while others focus on nouns or adjectives. It's like having a team of linguists working together, each with their own specialty.
I love that analogy. And by combining all those different perspectives, the model gets this much deeper understanding of the language.
Exactly. And it shows how the transformer goes beyond just processing words. It starts to get the nuances of human language.
Okay, let's switch gears a bit and talk about training. The paper goes into a lot of detail about how they trained the transformer.
It does.
What are some of the key things they did?
So they trained the model on huge data sets, like the WMT 2014 English, German, and English, French data sets.
Okay. Which are massive. Millions of sentences.
Millions. So they really gave the transformer a lot of data to learn from.
But with such a huge vocabulary, how did they deal with all the different words?
They used something called byte pair encoding, which basically breaks down words into smaller units, so the model can handle rare or unseen words better.
It's like teaching it the alphabet of the language, so it can figure out any word.
Yeah, kind of. And of course, training a model this big takes a lot of power.
For sure.
They used 8 NVIDIA P100 GPUs. Those are some of the most powerful graphics cards out there.
It's like a team of supercomputers working on it.
Pretty much.
Yeah.
They also use the Atom Optimizer, which is really popular for deep learning.
Okay.
And they used regularization techniques like dropout and label smoothing to prevent overfitting.
Right, so it doesn't just memorize the data, it actually learns.
Exactly.
And they even change the learning rate during training.
Yeah, they used a formula to warm up the learning rate at the beginning and then gradually decrease it,
Okay.
which is a common way to fine-tune the process and get better results.
So all these details show just how carefully they approached training. They really wanted to get the most out of this new architecture.
They did, and the results show it. It's amazing what they accomplished. But beyond all the technical stuff, I think there's something deeper about this idea of attention is all you need.
Yeah.
Such a simple idea, but it completely changes how we think about AI.
It's like they're saying we don't need all these complicated mechanisms. We can do incredible things with just attention.
Exactly. And that's had a huge impact on the AI community. So many new research directions have come from it.
It's like a total paradigm shift.
It is. It's like we've discovered a new principle of intelligence, and we're just beginning to understand what we can do with it.
But like with any paradigm shift, it raises new questions. How do we make sure we use this technology responsibly, especially as these models become more powerful?
Yeah, that's a really important conversation to have. Transparency, accountability, fairness, those are all essential for ethical AI. We need to be thinking about those things now.
Absolutely. It's been amazing exploring the Transformer with you. We've talked about so much, from how it works to the incredible things it can do,
It has been really cool.
and the big questions it raises about the future of AI.
Definitely. And I hope our listeners have a better understanding of attention now and how it's changing everything.
If there's one thing I want our listeners to remember, it's that AI is always changing. What's groundbreaking today might be old news tomorrow.
That's what makes it so exciting.
Exactly. So keep learning, keep asking questions.
Yeah.
The future of AI is waiting to be discovered. It's really amazing how fast the Transformer has, taken over AI.
I know, right? It's everywhere. And it's not just because it's faster or more efficient. It's a fundamental shift in how we think about AI. And that resonates with, researchers and developers.
When I first read about it, I knew something big was happening. But wow, I didn't realize how big.
The results were just so clear. Not only did it beat other models, but it did it in a way that felt right.
Yeah.
More elegant, more like how humans think.
It's like it cracked the code of language.
Yeah.
And it goes beyond just words and sentences.
That's the thing about attention. It captures those relationships between words, the nuances, the context.
It sees the big picture.
Exactly.
And that's led to all these new applications. BERT, GPT-3, DALL-E, all built on the Transformer.
Amazing, right?
They're generating text, images, even creative content.
And it all comes back to attention. It's a testament to how powerful and flexible this architecture is.
We talked earlier about how the Transformer's efficiency is similar to how our brains work, but these new models, like GPT-3, are kind of freaky.
Yeah.
They're so good at mimicking human thought.
It really makes you think.
Are we getting closer to AI that actually thinks like us?
That's the big question, isn't it?
Mm.
Philosophers and scientists have been debating this for ages, and the Transformer doesn't give us a clear answer, but it definitely makes us think about the possibilities and the implications.
As these models become more powerful, we have to think about the ethics, too.
Oh, absolutely.
How do we make sure they're used for good?
That's a conversation we need to have now before it's too late.
Transparency, accountability, fairness, those are all key.
Definitely.
This has been an amazing journey exploring the Transformer. We've learned so much about how it works, the things it can do, the big questions it raises.
It's been great.
And I hope our listeners now have a deeper understanding of attention and how it's changing AI.
Me too.
The world of AI is constantly changing. What's groundbreaking today might be old news tomorrow.
Yeah, that's what I love about it.
The Transformer is a perfect example. It changed everything. It pushed the boundaries of what we thought was possible.
And who knows what's next?
Exactly. So, to everyone listening, keep exploring, keep asking questions. The future of AI is out there. And thanks for joining us on this deep dive into the Transformer. We'll be back soon with more exciting deep dives into the latest research and tech.